Phillipson. This is Michael Rywalt. This is actually my master's thesis defense, so I didn't get to update these slides, so we're going to work off this. I'm going to go pretty fast at front because I want to get to a part that is more unique, that what makes this processor architecture unique. So let's go ahead and get started. So this is my supervisory committee, Dr. Stitt, Dr. Lamb, Dr. Eisenstadt, Dr. Schwartz. My name is Kevin Phillipson. My project responsibilities is the microarchitecture design, RTL, and microcode development. I got 15 years of industry experience in ASIC design. I got a bachelor's and master's in electrical engineering, and I'm currently pursuing a PhD from the University of Florida. My thesis, which is the topic of this presentation, is the development, analysis, and optimization of a compact and efficient microprocessor IP. This is Michael Rywalt.
And I also have 15 years of industry experience in ASIC design, software engineering for that, part of that. And my thesis for my master's is the verification of a compact and efficient microprocessor IP. I'm working on that right now.
Yeah. And then we also picked up some other team members. Boise Pete, I don't know where you are, Boise. There you are, the bad kid in the back. And Boise's been helping us with some of the benchmarking and testing compilers for the architecture. He's a PhD candidate at the University of Louisiana at Lafayette. His advisor is Dr. Martin Margola. Sorry. All right. So what are the goals for this project? So we're trying to design an open source professional level microprocessor IP. So most of the open source microprocessor IPs that you see out there on open cores are hobbyist projects. There's a few that really reach that professional level, like RISC-V or ARM. But we're not trying to build a RISC-V or ARM. So we're targeting, well, first of all, in today's industry, you have these big ASICs, big SoCs, right? And they have these large application processors, right? So ARM or RISC-V, four core processor. That's not what we're trying to compete against, because in these SoCs there's also a lot of other blocks, GPUs, storage controllers that need some level of high-level control. So we're trying to build a very, very small footprint but high-performance microprocessor IP. So what I'm trying to say is, think compact, think efficient, think different. This is not, we're not trying to go, to a full application processor. So, like I said, we're going to be trying to build something that's smaller. So we're going to look for a 16-bit architecture. So just to give you a quick, very high-level comparison between, a 32-bit and 16-bit CPU. So the typical application for a 32-bit or 64-bit CPU would be an application processor, whereas 16-bit would be a microcontroller. The 32-bit is going to have a larger die area, and the 16-bit is going to be a smaller die area. Now, given the same clock, that should reduce your power because you have less switching gates at the same frequency. Also, the 16-bit CPU is going to have a smaller memory footprint because it's going to have, obviously, smaller data precision as well as smaller instructions. Now, of course, on 16-bit performance, we should be about equal, but 32-bit performance, obviously, we're going to be performing worse. But that's the point, is that for the applications we're looking at, we're not, like, if you're doing a bunch of 32-bit math here, then this is not what you want to use. So tasks for a 16-bit CPU, obviously, like I said, if you're in an SoC, all the subblocks could utilize something like this. Design for test circuitry, manage like an interface parsing a data stream. So anyway, so the point is that if the task only requires 16-bit precision, then a 32-bit RISC CPU is a waste of area and power. So we're basically stating that there's a demand for a compact, high-performance 16-bit CPU with efficient memory utilization. So we had to choose a instruction set architecture. I don't want to go and define my own instruction set when I can go pick something up that's already out there. So I can take advantage of existing compilers, assemblers, and existing code base. But we want to be able to run C code. Okay, so we looked around, and I don't want to cause a holy war or anything here, but we chose the 6009 because if you really look at that instruction set, it was a clean slate design, and it's really it lends itself really well to C for having such a small register set, because it has these powerful addressing modes which map well to concepts such as arrays and pointers. And so why are we bucking the RISC trend? Well, like I said earlier, a tightly coded 1609 instruction set architecture is going to mean less area, which means less memory, which means less area. And the 1609 register set, I mean, this is what it is right there, is what is that? 1, 2, 3, 6, 7 16-bit registers compared to like a 32-bit RISC is going to have 32-bit registers. That's a lot of transistors, which is going to blow up your die area. So can we build an efficient RISC to assist to RISC pipeline microarchitecture? So that's a little hint of what we're going to be getting into. So professional level IP, what do I mean by that? Third-party support, assemblers, compilers, existing code base, that's already there. Use modern RTL design techniques and good practice, i.e., fully synchronous with a single clock, well-defined separation of control and data path, and separate the hierarchy out, and design for efficient synthesis into ASIC standard cell libraries and FPGAs. We're going to use an industry standard SoC bus. In this case, we're using the pipeline wishbone bus. And we're going to optimize for area, speed, and power. If you're an ASIC design engineer, this is what everyone talks about, right? Area, speed, and power. So we're going to be synthesizing into standard cell libraries and using that feedback in order to optimize our design. And a full verification test bench. This is huge. That's what really separates the hobbyists from the pros, and that's what Mike here has done a lot of. So, all right. So let's jump into the microarchitecture details. So here's a simplified representation of the microarchitecture. We have a fetch stage, decode stage, and execute stage, and a bus arbiter, and then the external part of the memory is also pipeline. So in this case, as shown here, it's a 6-stage pipeline. 1, 2, 3, 4, 5, 6. And you notice that this bus arbiter has internally, the architecture is what's called Harvard. So you have a separate program and data memory bus. And then externally, it's von Neumann. Now, I've actually created another bus arbiter that is Harvard externally as well, so you can double your bandwidth, but that's just a side note. All right, so let's look at the microarchitecture details. Again, I've been moving fast here. Sorry if I go too fast. I have some YouTube videos where I've reviewed this more in detail, but I want to get to the good stuff. All right, so the fetch stage. The fetch stage, basically, it's got, I wouldn't call it a cache, but it's a 8-byte instruction queue, so it is always looking ahead, but it's not a cache by any means. The pending transaction tracking, because what happens here is it's always basically trying to load instruction data, right? And so it has to track what requests are out on the bus, and interleaved into that are the data bus requests. So you need to track how many requests you have out on the bus in case you need a flush. And then the other note here is this FIFO here is a little bit unique. It's not a standard circular FIFO, it's a shifting FIFO, and the reason we do that is because we want to put all of the combinatorial logic on this side and just represent, just show registers on this side, because to reduce our timing paths over here, to reduce our critical path in the decode stage. So the decode stage is where the magic really happens. This is where you translate 6809 instructions into RISC micro-ops. So if you think about, if you relate this to the Intel x86 architecture, this happened around the 46 or Pentium. So at that point in time, they started actually taking just a purely microcode design and taking those micro-ops and pipelining them. So that's similar to what we're doing here. We use our own custom microassembler, which generates 16 blocks. So a classic microprogram machine is just going to have a microprogram ROM, and it's going to sequence through those. Okay, our microcode is different, where we do have a a sequential element, but we also have these other 15 blocks which decode directly off of the opcode. So we are basically utilizing parallelism from like at the microcode level. We don't have a ROM. We have like everything gets synthesized down to gates because of the way we're breaking things down. We're able to actually be more efficient that way. And this is something that Mike wrote, the microcode assembler. So again, this is not old school programming. I mean, old school microprogramming, and we think it's publication worthy. In fact, that's what my current task is to finish a paper and get that published. All right, so the execute stage. The execute stage, I mean, it's nothing it's not groundbreaking, but it's got some fancy features. It's got a full 16-bit ALU, full 16-bit address ALU. The address ALU is tailored to get those special addressing modes done as fast as possible in parallel. And the data memory controller is in fact another pipeline stage. It's like the write back stage, but I just don't draw it that way because I'm always drawing from a hardware level, not a software level. Okay, so some differences between the standard 6809 instruction set. So I lied. I did add a few extensions to the 6809 instruction sets, so we got wider divides and multiplies. We lifted these from the HC12, HC11. People are going to probably say, why didn't I lift it from the 6309? And that's because if I did that, I have to extend the register file. Whereas the HC12 has basically a very similar register file. It's actually smaller than the 6809. So inside the ALU, there's a independent sequential logic unit that can do these wider multiplies and divides. And it's nice because that allows me to parameterize them so that you can then say, okay, you can kind of pick your flavor before you synthesize and say, I don't need all these divides and multiplies, and then your design will be smaller. Another update is obviously the Turbo9 uses the Motorola 6809 instruction set. Now, if you remember, the 6809 was considered an 8-bit machine, 8-bit hardware, but its instruction set is actually 16-bit if you look at it. So the Turbo9 is a fully 16-bit machine, and I'll show you why. So anyway, let me just keep going. So the data path is 16-bit, right? The internal data bus is 16-bit. The program data bus is 16-bit. The external data bus can be 16 or 8-bit. It's configurable. And then the wishbone, we have different bus arbiters that you can put in place. So you can just do plain vanilla 8-bit. You can do 16-bit aligned or 16-bit non-aligned. What that means is that if you're in 16-bit aligned, then you have to, if you have a 16-bit word that's spanning a 16-bit boundary, you're going to have to do 2 writes, whereas the non-aligned is able to combinatorially pull that out. So the Turbo9 is a true 16-bit pipeline microprocessor with powerful 16 and 32-bit multiply and divide instructions. Let's look at the bus memory interface. So here's an oversimplified Turbo9, and then this is how you would set up your external memory subsystem. So you would have memories and peripherals and decode logic under that, and then decode logic for the read data back, coming back into the Turbo9. And so you have basically effectively pipeline stages, here and here, and you can actually pipeline these further. So if you're building a big system and you're starting to get your worst case timing path out there, you can actually further pipeline it, and you'll increase your latency, but you'll raise your Fmax. Wishbone compatible. So we offer it, like I said, in 3 different flavors. We've got the regular Turbo9 with the 8-bit external data bus. We've got the Turbo9S with the aligned 16-bit data bus, which will require 2 cycles for unaligned 16-bit transactions. And then the Turbo9R, which is our fancy racing version, and it's got 1 cycle 16-bit transactions. Now to talk about latency, so shown here, this is going to have a 4-cycle latency, 1, 2, 3, 4. But the cool thing about the external, the wishbone controller is that the way we built it is that it automatically adjusts for latency. So you can actually take out these pipeline registers and reduce your latency. You can parameterize these out as well and reduce your latency. You can run your memory, like if it's a synchronous memory, you can run it on the opposite clock edge, take out these registers, now you have a latency of 1. And the Turbo9 just figures it out. All right, this is where I wanted to be. Sorry I went so fast, but Morpheus is here. He wants to say, let me show you how deep the rabbit hole goes. This is the original Matrix, none of the sequels. All right, in order to do this, I'm going to give you a little bit of microprocessor design background. I'm going to show you an example multi-cycle 6809. This is not a Motorola 6809. This is just a theoretical 6809 for me to prove a point. In order to do that, the 6809 is going to have effectively the same execute stage. I'm using it as the data path here. So it's going to have 16-bit ALUs, 16-bit memory bus access, but it's going to be implemented in a multi-cycle fashion with a traditional controller: fetch, decode, execute, so on and so forth, right? All right, so here's a opcode matrix of the 6809, and so to prove my point, we're going to be looking at the add instructions. So you got add A, add B, add D, right? A register, B register, D register. The D register is 16-bit, and the other two are 8. And then you have your different addressing modes. So if you look here in the columns, you have immediate addressing, direct addressing, index, direct, and extended. Okay, and so here's a state diagram on how that would work. So you would have one cycle for fetch, one cycle for decode, and then there would be a split into which addressing mode you're going to do. So let's say we're doing 8-bit immediate addressing. We'd go fetch that data, and then we'd go to the execute cycle to actually do the function. So here it's A equals A plus the data memory, and then we'd come back. And then you would another path through here would be for indirect addressing. You would flow this way, and then you would go down to you would fetch your address that would then point to the data you're going to, right? So that's indirect. So you have an extra cycle that you jump down here, and then go to the execute state, and then back. And then here's for the B register and D register. All right. So going back to, let me just jump back. So this is what I'm talking about here. The state machine, basically. It's a state machine that's going to implement these cycles for each cycle of the instruction, right? So how do you typically implement this? So this would be, the classic way would be a synthesized state machine. So basically you got a register for your state, and that goes through some synthesized logic gates and feeds back what the next state is going to be, and sets the next state of the state machine. You have inputs, and you have control vectors that would go out into your data path to control your ALUs and such. So in this state diagram is just nonsense. It's just for me to prove a point. So for example here, you have state go, state A, state B, and end. You're setting your control vectors to some arbitrary value, and then you're making decisions on the flow of that depending on inputs. Let's talk about microprogram state machine. Okay, so a very similar idea, but what you're doing is you're effectively replacing that sea of gates with a ROM, and then you have something called a microsequencer, which is, if you're familiar with the AMD 2900 bit slice family, you know exactly what I'm talking about here. So you have what's called a micro PC, microprogram counter, which ends up being your state register, which drives the address into the ROM, and then some of the ROM comes out as your control vectors, and then some of it feeds back into the microsequencer to select your micro op select, your condition select to determine what condition you're going to be looking at, and then your branch address, and that way you can sequence through that ROM. And this is actually, the same. This ROM implements this state diagram, and you have a microprogram word. So this is like actually what's coming out of the ROM, and you basically slice up that word for your different vectors. So you see here on the end we have control vectors, and we could extend this microprogram word out obviously to be very wide, to have multiple control vectors, and then your micro op, your condition select, your branch address. This is what basic microcode looks like. So this is written in our syntax, but I'm not showing you any of the fancy features yet. But again, here is the microcode that would implement that state diagram. One thing about microcode versus assembly code is that, when you write assembly code, typically one line equals one instruction, whereas in microcode you typically have multiple lines and then some kind of directive to the assembler to say this is the end of the microprogram word. So you can see here, every time you see an end state, that's going to basically say, okay, I'm assembling that into one microprogram word. These mnemonics are actually macros. This is a macro assembler, and you define your macro assembler with a macro file. And what that's doing is it's basically breaking down these mnemonics into control vectors, okay? Which is what actually gets built into the ROM. So each one of these is control vectors, you know, that splits up the ROM word. I'm gonna just go ahead and we'll go to the next one here. So okay, so we've covered multi-cycle microprocessor. We've covered traditional state machine design. We've covered microprogram state machine design. Let's talk about pipeline processors. So the Turbo9 is a pipeline processor. It processes 3 adjacent instructions in parallel. And what it's doing is basically overlapping the fetch, decode, and execute. So if you got, you know, instruction A, instruction B, instruction C, they're all getting executed at the same time within the same clock cycle. From a software standpoint, you know, in the ideal case, this looks like you're executing one instruction every clock cycle, right? In reality, it's taking 3 cycles, but you're overlapping them. Now, obviously, if you read Henderson and Patterson, you know that RISC is wonderful and great and all that, and it works well for pipeline architectures. CISC is not the ideal case, okay? So I've been making a big deal about, you know, this elegant encoded 1609 ISA, but we're going to have to figure out how to map it onto a pipeline microarchitecture. So we need a CISC to RISC transition layer. And how are we going to do that? So this is the decode stage. So let's slow down. So you got your fetch stage over here on this side. So there's that instruction queue I was talking about. And you got your execute stage over here. And then this is the breakdown details. This diagram took me a week of my life to draw. And so what's happening here is, so you have your microsequencer. So we know what that is, right? And we have something called microcode. It's not a ROM. It's what we're going to call micro RTL. So this is actually going to be gates, but we're feeding it a address, okay? And then that's getting decoded out into control vectors, which end up in the next pipeline register, which feeds to the execute stage. All right, so that's all the stuff that you should understand. What's all this other magic stuff out here, all the green stuff? Okay, so these are decode tables, okay? So what's happening here, feeding into that, is the opcode and the page select. So if you look at the 6809 opcode matrix, there's actually 3 pages. There's a pre-byte that sends you to page 2 or page 3. So using that, like the opcode and the page select, we are basically directly decoding some stuff off of these 15 tables. So what are we decoding? Do I do that in the next slide? I'll explain here. So let's just take one of these for example. Let's do R1. So R1 is going to is a register pointer, and it's going to map into the ALU A select and the ALU write back select. So what that effectively is doing is that it's mapping, for example, in an add A, add B, add D instruction, it's going to basically tell me which register to use for that particular instruction. So I'm using the exact same micro code for multiple instructions, right? So I'm separating out that control from completely sequential microcode. This can just be decoded directly off the opcode and dumped into these tables. So there's 3 register pointers. There's R1, R2, and then there's a address register select. And then we have 2 jump tables. And the jump tables are basically to jump into sections of the microcode. So basically, I finished this instruction, and I need to jump to the next instruction. So coming off of the queue, the next instruction should be sitting here. Boom, this should give me the correct address from this jump table. Boom, and then jump into the correct spot in the microcode. Obviously, there's also stall logic, which is an unfortunate necessity of pipeline architectures, because you have to make sure that the next stage is ready before you can advance forward, or you have the data that you need before you complete that cycle. The micro RTL assembler, written by my man here, Mike, completely written in Scratch. Why didn't you write it in Python?
No, I'm a C programmer.
What's that?
There's still hope for C in the world.
Yeah, I agree. Yeah, that's as far as I go. So again, this is a macro assembler. So you're going to take your microcode file and your macro file. That's going to produce, like I said, the Verilog RTL for the microcode, the Verilog RTL for the decode tables, and then this is a nice piece. It generates statistics. So I got all these control vectors, right? I got control vectors to control the ALU operation. I got control vectors, to control the data memory operation. And so what the statistics give me is I've written all this microcode now to implement a full instruction set. And I want to be able to see how often am I using this particular equate for that control vector. And that gives me feedback to say, how am I encoding this? Like, is this the most efficient way to encode this? So that's what those statistics provide. So thank you, Mike. All right. So what does this micro RTL look like? Well, it breaks down into very simple Verilog case statements. And you say, well, that's not fancy. Well, it's really nice for synthesis because you're taking your complex problem, you're breaking it into simple blocks. Synthesis tools love that. And they just crunch in this, make it nice, compact, and small. So the micro RTL for the microcode basically has all these different control vectors that are controlled state to state. Like, for example, you can see the add instruction right here. We're doing things like this is the, let's get one that you can easily recognize. So the data ALU operation is A plus B. That makes sense. We're adding, right? And then we're setting one side of the ALU to R1. We're setting the other side of the ALU to R2. And then the right select is R1. So we're writing back to R1 because we're doing A equals A plus whatever back into A. And then we're setting our CCR Creedence Clearwater Revival register to whatever our CCR op is, and then this would be the condition input, which would be your carry in or whatever you're doing for a shift. The decode tables here are even simpler. You basically see on this side is the opcode, right? So here are all the different variations of add. So add A, add B, add D, but then all the different addressing. So direct, index, extended, so on and so forth. And you can see that they're mapping all the correct. So this is R1, so you're mapping A onto the correct ones, and D and B and all the rest of them. And then this is the jump table, which basically breaks down to the addressing mode because it's going to send you to the correct label in the microcode. So these comments here are automatically generated by Mike's microassembler. So these are the actual labels in the microcode. And so when it's like a two-pass assembler, right? So first you pass and you pick up, you figure out what all your labels equate to, and then you can use that to figure out the address in the microcode to go to. And here are the control vector statistics files. So what are we looking at here? So here's the data ALU operation. You can see I do a lot of adding. So A plus B. And so this is taking the entire instruction set and looking at it at that level. And so a lot of the times you're just passing stuff through the ALU, so you'll just do A plus 0, right, just to pass things through. So you use the add function there. There is no pass function on the ALU. The ALU is also obviously capable of A plus not B for subtraction, left shift A, left shift, right shift, and then some logical functions, and or XOR. And then this is the sequential arithmetic the sequential arithmetic unit, which does basically muxes in that unit to do the wider divides and multiplies. And then here's your this is for the R1 pointer, so you can see how often I'm using the B register, the A register, so on and so forth. And so anyway, I can look at this data and see how to improve my encoding, essentially. Okay. All right. So one of the big points I want to make here is so you look at this opcode matrix, right? So this is the 6809 opcode matrix. They did a very good job on mapping things logically, right? I don't know if you ever read, there's a paper by Terry Ritter and Joe Boney, who are some of the architects of the 6809. And they talk about how they analyzed the 6800 code. I'm sure they looked at 6502 code, but it's not in that article. And they looked at, you know, what instructions we want to add and then how we're going to lay it out. And so obviously all the register A instructions are grouped together. All the register D instructions are grouped together, and then the addressing modes are in columns. So when you give something like this to a synthesis tool, it's going to recognize this. And you know, if you take basic digital logic, you know, K maps, blah 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 blah, magic happens, and it's crunched down, and it makes for. My point is that you need to take advantage of this. Like if I didn't have these decode tables, I'm doing it in a classic microprogrammed way. I'm actually, what am I decoding this information from? I'm decoding it from the microcode address, right? Which has no relation to this table. So what I'm doing here is I'm exposing the opcode and decoding directly off the opcode to get this information. And by doing that, I'm making my design smaller because I'm taking advantage of their logical encoding into the opcode. If that makes sense. Okay. And so here's the jump table. So basically, I'm just showing you how there's like, so they're all color coded here. So you're showing like, okay, all these, you know, that are the same color are going to basically output have the same output. So they're going to be synthesized down a lot, and all the white spaces don't care. So the synthesis tool likes that because it can do whatever it wants. All right, so now let's look at our microcode given these decode tables. How do you write microcode and tell it, okay, I want you to decode this stuff in parallel? So again, we're using our favorite add instruction here to show this. And here is the microcode. So we're doing a data add R1 plus R2. We're writing back to the R1 register. We're setting the data width. So that's an important point to the width of R1. So if it's 8 or 16 bit, and then CCR operation, and then the jump table next PC is going to send you to the next instruction. Up here is where you break out the information for the decode tables. So for example, R1. So this is decode page one of the opcode matrix. Register 1 pointer, we're going to point to A, and then this is the opcode here. And then so on and so forth. R2 would be the immediate data. So we're adding A plus immediate data because this is the add A immediate instruction. And then the jump table, so what we're saying here is that I want to set the jump table to the add label right here for this opcode. And so when you do this jump table A next PC, you know, like we don't have fetch decode micro ops in the microcode because this is pipelined, right? So the fetch stage and the decode stage is taking care of that, right? So I just need to say, I want to go to the next instruction. So that's what that does. It basically says, go to the next instruction, and should go to the next instruction, and say, unless you flush your FIFO, and then it's going to stall and figure that out, but that's how that works. So basically this one micro cycle is all you need to do add A, add B, add D for all the different addressing modes. So let's compare our state diagram. So you're familiar with the one on the bottom. So how does this translate now for the Turbo9? So let's just start somewhere randomly. Let's just start in the execute state. Okay, so I'm at the execute stage. I just did add A immediate, right? And now I go jump table to the next operation. So it's going to come through here. This is not a stage, just a combinatorial decision, right? And it's going to figure out what the next instruction is going to be. And if it's let's just take which we'll do okay, so for the immediate case, it would jump directly back to the add microcycle, because the immediate data is actually part of the instruction, so that's actually going to be sitting in the instruction queue. So that would be a 1 cycle operation. So that would give our cycle time of 1. And then for like a direct, you would come through here. You would go through your direct addressing, and then to here. So that would be 2 cycles. And then for indirect addressing, you would go through the jump table. You would go into your index addressing and say, oh, no, this is just the address to the data. So then you have to go to that address, get your data, and then go to the execute state, which gives you a maximum of 3 cycles compared to our multi-cycle theoretical 6809 would have a minimum instruction cycle time of 4, maximum of 5, with a total of 15 different states that you'd have to put in your state machine, whereas in the Turbo9 state diagram, you only need 4 different states. So I love this. This is my favorite table. So what are we comparing here? Again, we're looking at all the add instructions just to make the point here. So we got the Turbo9R, that's our fancy racing version, and we got our example theoretical 6809, which has the same memory bandwidth as the same memory capability as the Turbo9, as well as the same 16-bit ALU capability as the Turbo9. And then we have the good old classic 6809. Here's all the addressing modes, cycle time, blah, 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 blah. Let's look at the bottom. So the classic 6809, for all the different combinations of the add instruction, can basically execute between 2 and 14 clock cycles. The example 6809 would be 4 to 6, and then the Turbo9 1 to 4. So I think that really summarizes. When I did my master's thesis, I understood all this work, how all this stuff worked, but I was really happy to be able to boil it down and explain it to this level, of how you get to the cycle timing advantages of the Turbo9. All right, let's get into. I'm gonna go fast through this stuff. This stuff is on some other YouTube videos, but I just want to give you guys the idea of the performance. I want to give some time for questions. So dry stone performance, where we're showing here different variations of the Turbo9, with different memory subsystems, 16-bit one cycle latency and so on and so forth. Classic 6809, Atmel AVR, and then a Pico RV 32 RISC-V, which is like kind of the smallest RISC-V implementation out there, and different variations of that. And then, so this is the clock per performance. So this is the DMIPS. So that's related back to, was it a VAX 7? You guys know what it is. But anyway, like there was considered a 1 MIPS machine. So you do some calculations and say, this is the effective performance clock for clock. And we can see that the Turbo9 is out here with about 0.7 DMIPS per megahertz. The AVR 0.4, and the classic 6809 is about 0.18. And then we have the Fmax per performance. So what that is that given a specific FPGA or a 7-nanometer processor or whatever, how fast can your design run? That means how efficient is not efficient, but how well designed is the microarchitecture to limit your worst case propagation path, so you can basically run it at a certain frequency. So you can see here that the Turbo9 with a 2 clock cycle latency actually achieves the best performance, because now you're balancing. You say, I'm going to give up a 1 cycle of latency for a higher clock speed. So you see here it's running 112 megahertz versus the 1 clock cycle latency is only running at 69 megahertz. So it actually achieves higher raw performance in that case. And again, we're beating out the RISC-V implementations. And the fastest RISC-V is running at 196 megahertz. And this is all in the same FPGA. That's the important part. You have to have the same processor, same FPGA in order to do frequency comparisons. All right, the competition. Let's not waste too much time here. All right, so we're talking about the Turbo9. We got the Motorola 6809. We got the good old Atmel or Arduino, whatever you want to call it, and then the Pico RV, and then we got the IBEX core, which is a really nice RISC-V implementation. They're kind of going against the ARM Cortex microcontroller solutions. And then of course you have the ARM implementations. I just want to point out a couple things here. So if you look at, so this is the, like, what I want to point out here, the memory bandwidth. Okay, so as all this data that we're showing here is a 16-bit memory bandwidth von Neumann. Okay, and where you look at the 32-bit Pico RV, it is going to have so that's a von Neumann 32-bit. So that has 32-bit memory bandwidth, whereas the IBEX core is going to have two 32-bit buses. So it's got 64-bit memory bandwidth. And the Atmel, for example, has a 16-bit program and 8-bit data, 24 megahertz, 24 megabit memory bandwidth. So my point is that we're able to achieve this performance through a smaller hose, right? A smaller pipe. That's because we have more compressed instructions. So if you compare like an AVR instruction set versus us, we're going to be more compact. Anyway, I'm going to glance over this. Sorry. So we did dry stone. We also did bytes sieve in C and assembly. This is where Boise helped out, and we actually looked at several C compilers. There's a GCC C compiler for the 6009 out there. There's CMOC, which is a really nice implementation for the 6009, and then there's VBCC. This is by a guy out in Germany named Volker Bartherman, and we found that the VBCC produced the best results. We were able to work with Dr. Bartherman and implement some of the extensions to the instruction set, and it's really nice being able to have access to him and talk to him about potential new instructions, because I'm a hardware designer. I am very afraid to add new instructions, because once you add new instructions, then I'm going to have to support them for the rest of the legacy. So talking to a compiler guy, I can say, what about this, what about that, or he can make suggestions. I'm going to very carefully add in instructions that only make sense, right? So dry stone performance, given the different C compilers. This is code size. So code size is the other mnemonic. So we had different optimization levels. We ran it with maximum optimization, but I'm just showing a lower optimization here that actually produces lower code size. Byte sieve, code size, Turbo9 in C is the smallest. Assembly, obviously Turbo9 is the smallest. I do lose one of these battles. Which one is it? Yeah, C. So byte sieve in C turned out to be larger than the AVR. And that's because, if you look at the GCC AVR compiler, it is really good. My point is that there could be some more optimization on the C compiler side for this particular one. Again, we beat them in dry stone, but not in byte sieve. So there's always, given your application, you can produce different results. But again, if you look at it purely on assembly, this shows you that given the assembly side, the Turbo9 is capable of producing the code for the Turbo9 would be smaller if your compiler can optimize for it. Area and power. So this is FPGA results. I actually have results in the 130 nanometer Skywater technology, open source PDK, and put myself in the spot here. RISC versus RISC-V, I think we're about 3 times smaller. There's a multi-cycle 6809 core out there. We're actually about even. We're actually a little bit smaller than that. So that just shows the efficiency of my design is able to produce the same size core, a multi-cycle 6809 implementation versus my implementations. Mine's smaller and faster. Versus the Atmel, I think we're about 75% of the size. Now that's just the core, For my paper I'm writing, I am actually implementing all these with their memory subsystems and their RAMs and ROMs, and basically then bringing in code size into how much the total die area would be. So that's going to be more representative of this number. So this is a little bit out of date. IP development kit. We started with Cadence tools, but then we realized that we'd have to rely on really expensive licenses if we, left UF. So we basically moved to purely open source tools, Icarus, Verilog. So we have to switch from System Verilog to Verilog 2001. Obviously, Mike here has done the microcode assembler, and then we use, GTK Wave, Xilinx with Auto for FPGA synthesis, and then Yosis. We're actually using OpenLane. OpenLane is a Skywater Technologies targeted ASIC design flow, so we're using that to get our area numbers, and hopefully we can actually fabricate this design before the end of my PhD. So professional verification. This is the test bench. So you have just a high level. You have a test bench, and then you have a behavioral model of a 6809. Then you have the Turbo9 RTL. What we do is we actually generate programs. So we say, okay, we're going to generate a test program for an add in instruction. So we basically build a 6809 assembly program, and we push random data into that instruction, and then at the end, what we do is we jump out and we dump everything back onto the stack, right? And then we signal back to the test bench that we're done, and then the test bench goes and compares those memories before and after. So we're able to see the state of the instruction before and after, right? And we're able to compare, given different directed and randomized tests, that the entire instruction set is working. So, high five. Okay. We got 24-hour nightly regression. So that's still running, Mike? I don't know if that's still running.
Actually, it's still running, and it fills up the disk. Yeah. So let's go back in there.
Yeah. Runs nightly, over 5, lots of fancy stuff. Yeah, right. Fully randomized inputs. Keep going here. All right, and this is the attributes list. We've actually updated this since then, so we're pretty close on full coverage. This is the tool set. So given a certain source, so you got your assembly, your C code, you put it through. For this example, it's a C compiler, and then you can target. You can target the FPGA or ASIC. You can target. We have the Sim6809 simulator that I've hacked to support some of the Turbo9 stuff. You can do RTL simulation. We can do behavioral simulation. The behavioral simulation also gives you waves, obviously, and it gives you a console output. We have a bootloader setup which will actually produce console output given if you're in this purely simulation environment, or the simulator will produce the same console output, or the FPGA itself, given a little VT100 terminal, will give you the same console output. So in summary, all this stuff. Basically, it's I'm pretty much done. I got a little bit of the interrupt hardware left to do, and the next thing that are pending, release the GitHub to the public. We took a while to get kind of our legal stuff out of the way and get the licensing done. So that's on my to-do list. Boise always reminds me, and then do some other more optimizations. One of the things is to publish this paper. So that's kind of my next priority. Get this paper published, and then come back, finish up the interrupts, do some more optimizations, write some more papers, maybe get a PhD. I don't know, but let's go. But in conclusion, the Turbo9. You say it, Mike. You say it better.
Turbo9 is a microprocessor solution for compact, high-performance applications where size and efficiency matter.
Yeah. Acknowledgements. My wife's support is amazing. My kids think I make robot brains. The late Dr. Lynch, I want to point him out as well. I mean, he's not on my committee because he passed away, but he was back in my undergrad days. He was a big influence that kind of sparked this craziness of microprocessor design. Joel and Terry Ritter, I've spoken to Terry. He actually came to my master's defense. They did a great job on the designing the instruction set. The Tandy Color community has been great. They've kept all this information alive and these tools alive, and thank you very much for doing that. And thanks for watching. Any questions? So we got.
How are you going to present this work when it's complete? Is it going to be IP kind of like ARM does, or is it Is it going to be
So,
provided in a different way?
so we're going to basically give you. It's going to be on GitHub. It's going to be our main place to get the official source. It's going to be a one clause BSD license. So basically, what that is if you redistribute it in source form, you have to retain the copyright. If you redistribute it in binary form, in other words, if you make a hard ASIC or an FPGA, you don't have to say anything. You can just go on your merry way. I don't care what you do with it after that. I will always be the official source for it. I'm sure there will be derivatives down the line. Yeah, it's not going to be. I basically want to put the most unrestricted license bar straight public domain. So it's just as long as you if you want to redistribute it in source, you got to retain my credit. But other than that, do what you want. Yeah, and that includes the microassembler. That includes the verification test bench as well. So it's not just the RTL. That's a very important note.
So I'm sure the real goal was to target like industrial
Yes.
applications, and but is there anything about it, like with the small die size, I guess it'd be cheaper to produce? Is there anything that lends itself to the hobbyist community?
Yes.
Does the 8-bit, the 8-bit external bus version, could it be pin compatible with the?
Excellent question. So, I'm doing a PhD, right? So I got to make this relevant to industry, and I'm targeting modern ASIC design. I'm trying to make it useful for them, saying, hey, why are you using that ARM Cortex M3 to do this task when you could do it with something that's way smaller, right? So that's how I'm making it relevant for, industry. And that's what's going to keep this, I'm passionate about this. I want to keep the 6809 and, the brothers and cousins, the 6502s and the 816s alive, the HC11s alive, and make them relevant for today. So that's where I'm focusing. As far as the retro community, I think you guys are going to basically take it and figure out how to put it into what you want to put it in, right? And I will support that. Now, what you want to keep in mind is, say you got a Coco, right, a Tandy color computer with a 6809. Could you just drop this in? You could make a custom ASIC or FPGA and put it in, but you got to think about what you're doing there. Everything around it is designed to run at 0.89 megahertz or whatever it is, right? And you're bottlenecking the Turbo9 within that system. Will it run faster? Yes. But is it going to really, show the performance advantages? So I'm looking at you, Brendan. So something like what Brendan has with the Coco VGA, if you can give the Turbo9 direct access to high-speed memory and a high-speed, stuff, and then maybe just have the keyboard and your other peripherals running on the slower memory subsystem, then you're going to see the advantages. So you're going to have to kind of divide and figure out how to make that where you make that divide. So does that answer your question?
Yeah.
Yeah.
Just to add to that, I'm concerned that even if it's clocked the same, reducing the number of clocks it takes to do something could upset your programs.
Yeah. Yes.
They have tight timing loops and stuff.
Yes. Yeah. So I had this conversation earlier today. You got to think. You remember back in those early '80s, people were writing games and just doing loops around no ops to get the timing right. That's not going to work, and that's going to be a downside. But there are other cores out there that do the correct cycle timing. I'm not trying to do that. Basically, if you look at it, I'm just trying to be instruction set compatible. Not bus compatible, though you could literally rip the bus interface I have on there and put an AMBA bus or an old school 6809 bus on it or whatever. It's very modular like that, so you couldn't do that. But yeah, so it's just instruction set compatible, not timing compatible. Yeah. So.
Is the clock internal or external? If you had it on the diagram, I missed it. Is the
clock external. Yeah. So yeah, one clock source.
So, a general problem that older architectures have, I imagine, when bringing in more modern processing, more modern techniques, such as what Lightning that are doing, is that they have usually a very small register file. And I imagine that you would suffer with a lot of read after write hazards when trying to just pipeline this and have to
Yes.
solve a lot.
Yes.
So did you find that to be a big problem in practice or not so much?
So I knew that going in. So if you look at a classic RISC pipeline, classic MIPS, it's 5-stage. Okay, there's a read and a write back and execute and so on and so forth. I went in knowing like that I wanted to avoid those hazards. So if you look at some instructions, like for example, I said the add immediate instruction would go in one cycle because it has no data dependency, memory data dependency, because the data is already within the instruction, so that can actually get through in one clock cycle. Whereas if it's a read extended or redirect, you're going to be 2 clock cycles. So what happens is the rest of the pipeline stalls, and the execute stage takes 2 clock cycles in order to wait for that data to come back. So I am basically off the bat giving up that deeper pipelining. Could you do deeper pipelining? Absolutely. But remember, my goal here is to be a small, compact processor. So there's trade-offs. So I just decide I'm not going to do it.
So internally, you're clocking at whatever the clock rate is. How does that compare to the outside world? Like, for instance, a 6809, in a single clock does address data. So the internal clock, are you running that, say, 16 times faster so that your bus rate is lower? Is the one cycle thing an internal clock?
Nah, it would so if you look at the 6809, you look at what's called for example, a 1 megahertz 6809 takes a 4 megahertz clock in, and it actually divides it into a quadric clock and does different stuff on different phases of that clock. But everyone calls that really a 1 megahertz 6809. So when I say 100 megahertz Turbo9, I'm saying that's 100 times faster for just the memory side, not the throughput performance. Its memory performance is going to be 100 times faster because on every clock cycle, I'm presenting an address and I'm expecting data back if it's 1 clock latency. Does that answer your question?
Kind of. Since you're pipelined, I would assume that your clocks were a bit faster. So
Nah. Yeah. It's all one single clock. Yeah, one single clock.
Follow up on that. So, with saying add immediate, how many microcode rows does that have to execute to completion?
For an add,
I would imagine a 4-cycle clock, like doing 4 microcode rows to finish.
1.
Okay, just 1 microcode.
Yeah, for add immediate, it would be 1.
Yeah.
For add extended, it would go into a micro op that is just for extended memory addressing, and then go to the second micro op to do the add.
Got it.
Yeah.
So that's kind of where I see a disconnect. Is like, so you say a micro op is 1 clock.
Yes.
But a complete instruction only takes 1 clock. So
Depends on the instruction.
Huh?
Depends on the addressing mode. If we're just like taking add, for example, add immediate 1 clock, direct or extended 2 clocks. Indirect would be 3 clocks.
Well, when you showed the microcode for the add, it seemed like there were 15, 20 micro ops happening in there or something. It was
The microcode or the state diagram.
I think it was microcode that you had shown like that. What is that?
So this is like, so you see this end state directive. All that is 1 micro op.
It's within 1 clock. Okay.
Yes.
All right.
This all.
Goes at the speed of the ASIC or
Yeah. In fact, this part here is the only sequential part of this. This is what's actually going to be assembled in the microprogram word, and then all these go into the other decode tables that are in parallel. It's not just 1 microcode ROM. We have effectively 16 microcode ROMs.
So that's 1 micro program counter step.
Yes, exactly. Yes. We're done? Cool. Thanks, guys. Appreciate it.
Thank you.